In chapters 21 and 22, we're going to look primarily at bonding in transition metal complexes. So we're going to talk about how bonds are formed by Lewis acid-base chemistry. We're going to talk about coordination number. We're going to talk about isomerism. And then finally, we're going to talk about nomenclature, how to name the compounds. Now, in chapter 22, this chapter is based on bonding in solids. I am going to give you a little introduction to this in a short video, but it's a little difficult to explain at the general chemistry level, so we're going to let you guys read that chapter. I'm going to give a little introduction to it, which you'll watch in a video, and that should be enough to get you ready for the final. So this is what we're going to be looking at in chapters 21 and 22. In this video, we're going to look at coordination complexes, and we're going to look at most primarily structure and isomerism. So this is chapter 21, and what we basically recommend with chapter 21 is that you read the chapter and go over it yourself, and then we're going to highlight some of the more important sections for chapter 21 in this video. The same is going to go for chapter 22. I'm going to create a video, and with chapter 22, we basically just suggest that you read the chapter and you take a look at the video and do your best to understand what's going on. So with coordination complexes, we have to kind of remember what the story is with coordination complexes. So when it comes to a coordination complex, what we have is a Lewis acid-base type chemistry happening. So if you remember, if we react silver ion in aqueous solution with ammonia in aqueous solution, and they form a complex. So we saw this complex in lab where they form the silver ammonia complex. And what we said was in our discussion of this back in chapter 17, we said that the formation of these compounds is due to Lewis acid-base chemistry. So we have a Lewis acid and we have a Lewis base. And the way this bond forms is that silver ion has a lack of electrons and ammonia has an electron pair which it can donate to the silver. And then this electron pair is what actually forms the bond. So the AgNH3 bond that's formed comes from the electrons that were on the NH3. So the NH3 donates its electrons. And the resulting complexes can be cations, like this one is a cation. They can be anions or they can be neutral complexes. So you can wind up having a coordination complex that is any one of those three. Now, another thing we have to understand is the coordination number. So what this is this basically tells you the number of bonds that form between the central atom and the ligands. So this doesn't include double bonds. This is just the sigma framework, kind of like how we did this with Lewis structures. So if the central atom has 4 things around it, then its coordination number would be 4. So typically the coordination numbers are 2, 3, 4, 5, and 6, with 4, 5, and 6 being the most common. And so in terms of geometry, in terms of the molecular geometry, we're going to follow VS-EPR rules. So 2 would be linear, 3 would be trigonal planar, 4 is going to be tetrahedral, 5 is going to be square pyramidal. Oh, no, I'm sorry. That's going to be trigonal bipyramidal. And then 6 is going to be octahedral. So this kind of gives an overview of coordination complexes and what we're getting at with that. So now let's talk about structure and isomerism. So isomerism is where you can have. So isomerism in isomerism, you have the same number of ligands and the same type of ligands, but they're in a different geometric pattern. So they differ by some kind of structural difference, not by some kind of stoichiometric difference. So we have a couple of different types. We have structural isomers. We have structural isomers. And there are a couple of different classes. So we can have ionization isomers. And so this is something where this is a situation where you have a different anion coordinated to the metal. So let's take a look at one example. So here we have a cobalt complex where we have cobalt, and in the coordination sphere, what's bound to the cobalt is 5 ammonias and 1 sulfate. And there's a counter ion that is bromide. So just to remind you guys that inside the brackets, this is the coordination sphere. And these are what's bound to the metal. And then this is the counter ion. So that's not bound to the metal. That's outside, and that's like a salt. This would be the cation, and then this would be the anion, the bromide. So with a ionization isomer, we could have the following. We could have cobalt, NH3, and then we put the Br inside the coordination sphere and have the sulfate on the outside. So again, there's the same quantity of ligands and molecules inside of this structure. It's just that they vary by which one is bound. So this one has the bromine bound, and this one has the sulfate bound. So what you would notice is if you were to do for example, if you were to take this and dissolve it in water, and then add like silver ion to it. So if we were to have this dissolved in water and then add silver, what would happen in this case is the silver plus the bromide would react to give silver bromide, because the bromide is decoupled from this in solution. So when this thing dissolves in water, the bromide comes off, and we have our coordination complex that's over on the left. We have our bromide that's free and separate because it's floating around as the counter ion. So the silver would react with the bromide to form silver bromide. Whereas in this case, the silver would react with the sulfate and give silver sulfate. So we would get two totally different precipitates of silver depending on which ionization isomer we had, because the counter ion is not physically bound to the coordination complex in solution. That comes off and acts like a regular salt. Okay, so the second one we have is hydrate isomers. So if you guys remember back, we had this idea of a hydrate. So hydrates were compounds that had water, and the water is encapsulated in the crystal structure. So there's a stoichiometric relationship between the salt, like cobalt chloride, and then if we have hexahydrate, we know that for every 1 cobalt atom, we would have 6 water molecules, because there's a definite locking of that water into the crystal structure in a stoichiometric way. So in this case, these are going to differ by the placement of water molecules. So let me show you what this would look like. So we could have a chromium complex with 6 waters in the coordination sphere, and then have 3 chlorides connected as counter ions. The isomer for this would be as follows. What we could do is we could take out one of those water molecules, and we could have chromium H2O2, and then only have 1 Cl and have 1 Cl on the inside, and then we would have 2 Cl counter ions, and then we would have dot H2O. So here, I'm sorry, this should be 5, just so that we have balance, because this is still an octahedral complex. Oops, so I made a little mistake. Right. So what we're doing is we're basically moving a chlorine into the coordination sphere. And when we do that, one of the waters comes out and becomes now a water of hydration. So these would be two totally different structures. They would have different crystal structures. And we could actually differentiate between these two by spectroscopy. So that's important. Okay, so the next one is going to be a coordination isomer. And so these are where you have complexes that vary by... So in essence, what you have is you have two complexes that are linked together as a salt. So it's a little bit of an unusual situation, but it's something to think about. So let me show you kind of an example. Let's say that we had copper ammonia 4, and this was our cation. And then our anion is PtCl4. So this is our cation complex, and this one is our anion complex. And it just so happens that we've precipitated these two complexes together as a salt. Well, what you could do is you could move around those chloride and ammonias and get the same exact stoichiometry, but with a different complex. So, for example, we could put the ammonias on the platinum, and we can have platinum ammonia 4, and then we can have CuCl4. And so the complex is different because now the ammonias are bound to the platinum and the chlorides are bound to the copper, but overall the stoichiometry remains the same. So that's what we would call a coordination isomer. Now this one is a little less common, but is something to think about because, again, it definitely is a way that you could have the same stoichiometry. Now, the last one for structural isomerism is what we call a linkage isomer, and this happens quite frequently. So this is where you have a ligand that can bond from two different atoms. So, for example, you could have NO2 minus, or you could have SCN. And if you draw the Lewis structures for these, for NO2 minus, you get something that looks like this. And for SCN, you get something that looks like this. So what you could have is you could have you could have the nitrogen acting as your Lewis base, or you could have the oxygen acting as your Lewis base. And so these could link in two different places, meaning you could have a platinum bound to this NO2 minus from either the nitrogen or from the oxygen, and that would give you two different structures, but yet you'd have the same stoichiometry. And the same thing goes here. You could have this be act as your Lewis base, so you could have the nitrogen act as your Lewis base, or you could have the sulfur act as your Lewis base. So again, you could get two different ways that this could bond either through the N or through the S. So those are linkage isomers. Now the next main category is called stereoisomers. And so with stereoisomers, we're not changing the way things are coordinated. In this case, all of the atoms that are coordinated will still be coordinated. So now we're talking about within the coordination sphere. All the other ones were sort of outside of the coordination sphere with the geometric isomer, with the coordination isomers. So now with geometric isomers, the atoms bond in the same way but occupy different relative positions. So let me show you what I'm talking about. So one possibility is we could have, if you take a look, we could have this complex, platinum, ammonia 2, chloride 2. So we could draw this one way, where we basically take platinum and we put the ammonias across from each other, and we put the chlorides across from each other, and we get something that we would call trans. So the reason why this is trans is because the ammonias are opposite of each other, and the chlorides are opposite of each other, and so we get one type of structure. Now, in another type of structure, we could take it and we could say, well, okay, let's put the chlorides next to each other, and then the ammonia next to each other. This one would be called cis, and the reason why it's cis is because the chlorides are close to each other. So you can kind of remember that. Cis is close, trans is far. So these are going to have different spectroscopic properties because the coupling between the chlorides is going to be different when they're across from each other or when they're close to each other. So this is called cis-trans isomerism. And we can do the same thing with cis-trans isomerism with a octahedral complex. So if you look at this octahedral complex, now I'm going to draw this so that it is three-dimensional. So this is an octahedron, and we have to remember that these things are basically two square pyramids on top of each other. So in this complex, we have an iron bound to 4 ammonias and 2 chlorides. So in the square plane, we have all 4 ammonias, and in the axial positions, we have the chlorides. So this, we would call this one trans, because all of the atoms are trans to each other. But we could change this around a little bit, and we could put one of the ammonias into the axial position, and then we would have the cis case. Where now the chlorides are 90 degrees from each other instead of 180 degrees. So in this case, chlorides are 180 degrees apart. In this case, the chlorides are 90 degrees apart. And so that would be the cis-trans case for an octahedral. One thing you should recognize is that there's no geometric isomers for tetrahedral, just so that you're aware. You can't do it because of the symmetry of tetrahedral. This only works in square planar, octahedral. It could work. It can't work also in trigonal planar. So you have to think about the symmetry, because when you have these complexes, the symmetry considerations become quite important. We're not actually going to talk about symmetry in Gen Chem, but if you were to take an inorganic class, an advanced inorganic class, you would talk about symmetry. The last thing we're going to cover for this chapter, besides nomenclature, which is going to be a separate video, is polydentate ligands. So these are ligands that can bond through more than one lone pair. And so they'll form multiple bonds. So an example of this is ethylene diamine. Which has a structure that looks like this. And so these two lone pairs can bond to a copper atom, and what you get is the copper atom, this would be copper 2+, bound to 2 of the amine groups of the ethylene diamine. So this comes in and grabs on, and it grabs on through 2 groups, and this tends to lead to an unusually strong bond. Because basically what would happen is like, let's say one of the amines pops off, and it, remember these things are in equilibrium and they have a formation constant. So if one of the amines pops off, the other amine is there holding it on until the amine can find its way back and rebond to the copper. So this tends to lead to a very, very strong complexation. And oftentimes we use polydentate ligands to chelate metals that we want to take out of a aqueous solution, for example, or out of the body. For example, if you have lead poisoning, they use very strong chelating agent, which a chelating agent is it's basically a polydentate ligand on steroids. So it's a chelate agent would have maybe would be polydentate but have 3 or maybe 4 or maybe even 5 points where it will bond to a single molecule. So that bond's super duper strong, and what it does is it takes that molecule and makes it and gets rid of it. It helps the body to get rid of it. So they use chelating agents to get rid of like things like lead from water, or to get rid of lead if you have lead poisoning. So that's why polydentate is important, because you form a very, very strong bond, and it prevents that metal ion from getting out and escaping into solution. So this gives an overview of coordination complexes. The next video, we're going to look at how to name these complexes.